Hello everyone, welcome back to the lecture series on semiconductors. I am Dr. Atasi, Assistant Professor of Physics, Humanities of Science, MLR Institute of Technology. So today I will discuss about direct and indirect bandgap semiconductors. So already we have classified semiconductors into intrinsic and extrinsic semiconductors. Again, here on the basis of the energy bands, we will classify those into again direct and indirect bandgap semiconductors. So today in this lecture, I will go through EK relationship, then direct bandgap semiconductor, then indirect band semiconductor, and I will summarize this topic. So now I will start about this EK relationship. So energy spectrum of the electrons which is moving in a periodic potential, so it can be divided into allowed and forbidden zones. So this thing we have already studied according to the band theory. So here according to the zone theory or Bloch theorem, all the electrons will be moving in a periodic potential. And then after we have discussed in Cronin-Penny model that if electrons are moving in a rectangular squirrel potential which is also periodic in nature, then we can get a relationship between the energy and the wave vector. So there the energy is dependent on the wave vector. So if we will vary the wave vector, then the energy value will also be varied. So from there we have got some relation between the energy and the wave vector value. But in real crystal, the energy and wave vector dependence, it will be depending on something else also. What is that thing? That thing is the direction of the crystal. So it will be dependent on the direction of the crystal also. So here the internal potential energy distribution will vary with the direction of the crystal. That's why the EK relationship will be much more complicated. This is the reason where this EK relationship will be modified a little bit. So before we know that the outermost energy band is the valence band where electrons are there. So we are having valence band, and outside the valence band we are having our conduction band. So we are having conduction band. And when electrons, the outermost electrons will move within this band, that times we can see various electronic properties of a metal. And the gap between this valence band and conduction band is known as our energy gap or band gap. So mostly we see that these are parallel bands we take in general to see a representation of this. But in real, as I told, this EK relationship will be modified a little bit due to the variation of the internal potential energy with the direction of the crystal. That's why this energy and wave vector relationship will be modified a little bit. That's why without being parallel lines, this will be like curves. So here we have classified the semiconductors into two categories like direct bandgap semiconductor and indirect band semiconductor. And again another thing I want to mention here, so the intrinsic semiconductors, those are classified into this direct bandgap semiconductor and indirect bandgap semiconductors. So now we will look at this direct bandgap semiconductor. What are these direct bandgap semiconductor? Now I have already told you that this valence band and conduction band, those won't be like straight lines and this will vary with the wave vector. So now in x-axis I have taken the wave vector and along y-axis we are considering the energy. Now as I told, the valence band and the conduction band, those will also vary with the wave vector. So now you can see here, this is the top of this valence band. the curve represents the top of the valence band, and here this curve represents the bottom of the conduction band. If the bottom of the conduction band and top of the valence band, this lies at the same value of the wave vector, then this type of semiconductors are known as direct bandgap semiconductors. Here you can see that we are getting a variation in this conduction band and valence band, where the bottom portion, the most bottom portion lies for the conduction band, and where the most top portion lies for the valence band. Those two energy values, if those two are lying for the same value of the wave vector, then this is known as the direct bandgap semiconductors. So here we can see when electron is moving from valence band to conduction band, then in conduction band we are having electrons, and in valence band we will have holes. Now as these two, like the top of the valence band and bottom of the conduction band is at same value of wave vector, so here this electron and hole will be recombined easily. That's why when electron and hole will be recombined, what will happen? So we are getting one electron and hole. Hole will be represented as nothing but a positively charged, like it will have same mass as electron, but it will have positive charge. Then what we will get? We will get one photon of energy h nu. So now photon will be produced. Now due to this recombination of electron and holes in the direct bandgap semiconductor, we will get one photon. So that's why here directly, as at the same value of K, this conduction band, bottom of the conduction band and top of the valence band exists. That's why this lifetime of the charge carrier will be very less, because very easily this electron hole recombination will take place. That's why the current amplification will be also less, because the lifetime of the charge carrier is less. That's why current amplification is also less in case of direct bandgap semiconductor. Then what are the other properties? Then this will have high optical absorption coefficient, and that's why, as I told, photons will be produced when this electron hole recombination occurs in this type of semiconductors. That's why it will be very suitable to make optoelectronic devices such as LEDs and laser diodes. So some example of such type of semiconductors are gallium arsenide, indium phosphide, cadmium sulfide and magnesium oxide. So these are some compound semiconductors we can see. So already we know about the definition of intrinsic semiconductor, which are the pure form of the semiconductors. So in the lecture 1 I have discussed about this. So in that I have separated like some compound semiconductors and elemental semiconductors. So all the compound semiconductors, these are nothing but direct bandgap semiconductors. So we can use this type of semiconductors for the construction of LED, laser diode and all. Okay. So next we will go to the indirect bandgap semiconductor. So what are indirect bandgap semiconductor? So direct bandgap semiconductor, the top of the valence band and bottom of the conduction band occurs for the same value of the wave vector. Here the case is different. That's why here the top of the valence band, so here I am having my valence band and this is the conduction band. So here the top of the valence band and here the bottom of the conduction band lies. So these two lies, these two, top of the valence band and bottom of the conduction band, these two lies for different values of the wave vector. This type of semiconductors are known as indirect bandgap semiconductors. So how electron-hole recombination occurs in this type of semiconductors? So here the mediator will be phonons. Phonons are nothing but those are the quanta of lattice vibration. So through lattice vibration, these electrons from the bottom of the conduction band and holes from the top of the valence band, it will come to a particular recombination center, and at that recombination center, electron hole will be recombined, and that time some energy might be produced. So there are we will have some non-radiative recombination, we will have some radiative recombination also in this case of indirect bandgap semiconductors. And here, as I told, this will be mediated by phonons. This will be mediated by phonons, which are quanta of lattice vibration. So here, this energy will be lost by the emission of phonons. Because of that, heat will be produced. In the previous case, in case of direct bandgap semiconductor, light will be produced, but here heat will be produced. And here, as lifetime of the charge carriers are more, because the charge carriers, which are the holes and the electrons, they need to come to the recombination center, then after only electron hole recombination will occur. That's why the lifetime of the charge carrier will be more in case of indirect bandgap semiconductor. Then that's why the current amplification will also more. And this will be used to manufacture diodes and transistors. And these indirect bandgap semiconductors will have low optical absorption coefficient. So this is all about indirect bandgap semiconductors. And yes, the example for this are like all the elemental semiconductors. Those semiconductors which are the elements of the periodic table, like silicon, germanium, which are in the 14th group of the periodic table. So all the elements in the 14th group of the periodic table, like silicon, germanium, etc., those are the example of indirect bandgap semiconductors. So now the summary of this talk. So I have discussed about direct bandgap semiconductor and indirect bandgap semiconductor. Indirect band semiconductor, top of the valence band and bottom of the conduction band occurs for the same value of wave vector. For indirect bandgap semiconductor, top of the valence band and bottom of the conduction band occurs for different k values. And here direct and indirect bandgap semiconductors have distinct properties and applications, which we have already discussed. So if we will understand this difference between this type of semiconductors, then it will be very much useful to design optoelectronic devices. So this is all about the classification of these semiconductors according to the band gaps into direct and indirect bandgap semiconductors. So thank you. So we will discuss about LEDs in our next lecture. Thank you.